it's almost ever elusive, right? It's
Exactly.
the fact that we actually do have this somewhere within the weights if we maybe just look or can
It's like
model this
Atlantis,
in the right way.
It's like where people...
Yeah, that's right.
But unlike Atlantis, we know that it is true that you could find a much smaller model that performs the same as a big model. But it's like, how do you get to this like promised land? Hey guys, welcome back to the Pre-Trained Pod, where AI scientists talk shop and also occasionally talk shit. My name is Richard. I still am a AI research fellow at the University of Cambridge, but also now research engineer here in the Bay Area. With me as always.
Hey everybody, I'm Pierce Freeman, AI founder based in San Francisco, and I'm very happy to have Richard back in the Bay.
We're back, baby.
SF is so back, baby.
SF is so back, dude.
People have been saying it for a while now, but now it's really for real.
We're so back. Is that just from OpenAI when they obviously closed and then, Sam Altman got ousted and they came back? Like, I feel like they really took that phrase, and I've been hearing people just like using that. People are so stoked about SF. It's incredible. And I gotta say, dude, like the city feels beautiful. Like I am so bullish on SF again. Not just for like the whole AI stuff that's happening here, but just like the vibes in the city are great, dude.
Mm-hmm.
I was at Tunnel Tops, like the new park.
Unreal.
Yeah. And it's such a good job. In another life, dude, I would love to be a park designer because whoever designed that park, dude, should get a promotion. Like,
it's
that
spectacular.
Was incredible.
You've got views of the bay, views of the bridge. It unfurls down to Crissy Field.
It's beautiful.
I looked the other week at the Parks Department budget in San Francisco, and for how little we allocate to them, I think it's something like SFPD, 45% of the budget.
Oh, wow.
You know what I mean? Parks Department, like 3%. Let's move a little bit of that just into that.
All parks, dude.
I would say all
SF,
parks.
SF just
little
becomes
bit
a
more
park.
Parks.
Yeah. Dude, it's unreal. Like they've done such a good job with the city. I feel like it's really becoming much more European in some sense. The one thing that I think Europe has also done really well is whoever like was like designing the cities back in the day, like the 1900s, had the foresight to be like, hey, you know how Lord Pierce has this big farm with this big park? Why don't we just not touch that park and leave that be a park? And so in Europe, you'll just have like random like big green spaces that used to be some like rich dudes hunting grounds, but they've just kept it as like a beautiful park now.
Well, I guess the real question for this episode, Richard, is do you know how that works in China?
That's right. That's a great pivot, dude. I was just, honestly, that's good. I was about to just keep, going about this. I feel very passionately about parks, dude. China, notoriously, well, I don't know if they have great parks, honestly. Last time I was in Shanghai, I don't think they've really developed a lot. Like the park culture isn't really as present there. But what is present in China?
Ton of frontier labs.
New frontier labs that somehow are all tied up with like a quant firm as well. Like,
yeah, true.
Randomly, you know what I mean? But anyway, they not just have good frontier labs, they also have and are coming out with brand new interesting styles of language models. And I want to talk about this because I think it's really worth double clicking on what's going on in China, because it's so easy to just not really expand our scope beyond US frontier labs, but there's a bunch of interesting stuff happening in China. And one paper I want to talk about to you today is the Manifold-Constrained hyperconnections paper. So this paper actually dropped on New Year's. They dropped this like pretty incredible paper that has been making the rounds. And the reason that it's so exciting is because unlike most papers, the Manifold-Constrained hyperconnections paper, or MHC for short, is basically a brand new model architecture. It's still using transformers as the backbone, but it's a new architecture in the sense that it changes one of the core components of transformers, which are the residual connections, in a pretty big and meaningful way. I want to get into all of that at some point, but why don't we start with the basic building blocks of transformers to understand why this MHC stuff is so interesting. Okay. And so in order to understand that, I think it's first talking about what's the deal with residual connections in transformers. And once we understand that, I think then it's a pretty easy stone's throw away to just explain why we need something like MHC in our models. So let's start off by talking about like residual connections. What are they, man?
What are they?
What are residual connections?
What's good with these residuals? I actually think we've kind of come full circle and we're just obscuring what they actually are by calling them residual connections. It's as simple as just doing a plus operation of f of x plus x. That's all that a residual is.
And what's X?
So yeah. So I'll get in that. It came originally, actually, if you remember back in 2016 with the ResNet paper, which stood for residual networks.
Yeah.
And this was the big innovation that the paper really brought to bear. Like I said, in hindsight, pretty obvious. So it's kind of this idea that within all of these different neural networks, we try to think of them in terms of layers of these reusable building blocks, right? So like the transformer is like a layer in this network, but you can have other layer types as well, like a linear layer that's just a projection from one size to the other side. Or you could have some normalization layer. So it's like these reusable things. The art of actually making the architectures is just recombining them in novel ways to do novel things.
I think it's important to say, like, when people say like, oh, it's a transformer model, what they really mean, it's a model that's composed of transformer blocks. The blocks themselves are the transformer, and we stack like 12 or 20 or 50 of those to make a transformer model. The innovation is like each of these blocks are basically like a little Lego piece that you just put on top of each other to build an arbitrarily big structure. But the innovation is like the actual blocks themselves.
Yeah.
Right?
You can kind of think of it this way, right? It's like you're aware of how the Panama Canal runs, at least roughly, right?
Uh-huh.
Are you?
Yeah, there's like series of like locks, right?
Yeah.
And like little lakes and stuff.
Exactly. So you can almost think of going through a network as going through the Panama Canal from one side to the other, right?
Okay.
So your boat comes in. Your boat's being like the sentence, you know what I
Yeah.
mean? But let's think of a boat for now. It goes in, you have to get it to a different level. Like you're actually trying to like increase some elevation a little bit.
Uh-huh.
So you like fill this lock, you get it up to the water level of the next part of the lock, and your boat moves on. Each individual one of these locks that are like raising or lowering dimensions, as we're thinking about them, sometimes keeping it the same, is the transformer layer or block itself. But basically this idea is that within each of these blocks, you almost don't have to know what's happening within them. The fact is like we're manipulating the numbers in some way. Like we're trying to raise the lock to some other level, do some things within the lock. But by the time that it gets to the second lock, we don't really care about what happened in the lock before. We just care that they're there now. So the residual connection is you're trying to keep a little bit of the water from the previous lock into your current one.
Okay.
And that's how we're flowing. So it's
I think
like
that works.
a way
Yeah.
of keeping some of the information that
Yeah.
you've continued to accrue over time. Even if this lock is like changing, levels and parameters, you're still trying to keep some of the memory of what happened way earlier when you first got into the canal by the time you get to the very end.
Right. I think that's a good metaphor. Maybe you could imagine like the different locks are each of the transformer blocks, and you have like a little river kind of connecting them, right? A little stream connecting those two together. Okay, so that's a residual connection. And so like, why do we use them in the first place?
I think it speaks to the fact that one, they work better empirically in practice, right? Like the models that are developed with them have better accuracy. And that is because of the gradient flows that come through this network. It ends up being a lot easier to keep non-zero gradients. So what is a gradient? It's basically saying the optimization that we're trying to run is if it starts at all these random numbers that are just in this soup of these matrices, what we're doing through this optimization process is we're trying to move those numbers in a direction so that the end result is what we want. And I think my lock metaphor might break down at this point, but I think effectively we're trying to like control the levers of these locks to actually get them in the right place, right?
Yeah.
And we're trying to like dynamically adjust that based on seeing more data. So the gradients in practice that are flowing through these networks, because they're big, end up being reduced the further back that you get typically. Because if you're multiplying something small by something else small, that's going to be small, but then you do that 5, 10, 100 different times, it's going to be minuscule. You know what I mean? And that's why a lot of these early networks that we were training could only get so big and their accuracy would deteriorate once they got to a certain size. Residual connections kind of ended up being the solution to that problem of saying, because at each step, whenever we're done with the layer, we're now recombining it with what came into that layer. At each time step, you can kind of arbitrarily adjust that thing with the same magnitude as you would adjust the other thing.
Yeah. Something that has to be said is like the bread and butter of training a transformer is gradients, right? So like gradients are what basically send the signal to the model to say, this is how you should update in order to get better. And so if we do that 100,000 times, the model eventually will have seen 100,000 gradients and it'll have improved 100,000 times over. And so you end up with a great model, right? But the issue with the gradient fundamentally is that We say gradients flow because they basically flow from the top to the bottom of the model, right? They kind of like trickle down. It's kind of like trickle down economics.
In that it doesn't really work.
And
in
it
practice.
doesn't really work sometimes. Yeah, exactly. Yeah. So basically what happens is like you have your model, which is like, I said, these like stacked Lego blocks basically. And at the very top of the stack, that's where you receive the first signal for how to improve. And so then the first block sees the raw signal, and it then basically tells the block beneath it, hey, this is the signal that I got. This is the signal I'm going to give you. And it's like a game of telephone from the top to the bottom. And just like in the game of telephone, what can happen is if someone gets the word wrong and passes on the wrong signal, each of the subsequent layers are going to get like a messed up version of the original signal. What the gradients experience is basically like a degradation in the purity of the signal as they go down. One way to fix that is by basically having a residual connection, which is a way for the networks to interact in a way that they always have access to the clean original signal, no matter at what layer of the block you are. So imagine a game of telephone where you're maybe like the 10th person in line. If you're just taking the person before you's input, that might be a little noisy. But if you somehow had access to the original word that was said as well, then it doesn't really matter where in the lineup you are. You're always going to know what the original kind of like signal was, right? And that's what residual connections let you do. So they kind of like let the signal propagate down the model in a way such that no matter where you are in the model, no matter what transformer block you are, you're always going to get the original correct signal, right? And that is obviously very important for the model because these transformer blocks, they all have to work together, right? If the first block gets something wrong, then all subsequent blocks get it wrong too. So having access to the correct signal is really important.
And I do think that, even aside from the metaphors of like why this works and like introducing gradients, thinking about this at an algebra 2 level, at least that's what we say in the States. I don't know how it, like the corollary, but like, second year of like high school, having it just like a function that manipulates some input added to the initial input is the formulation that I still think of when I'm thinking about these layers. It's just, in reality, you're having to make sure these matrices line up in some 3D tensor space. But like the arithmetic is actually the same as just doing like a simple plus operand on some like smooth linear function that you're able to graph with an XY.
Exactly. Yeah. I mean, coding up a residual connection is actually super easy.
Totally.
Because as you said, it's just like, it's literally an add. Yeah. You just add the input to the output, basically. That's all that's happening here. Okay. So what's the issue with residual connections, or what are some of the downsides? Okay. So one of the fundamental issues with residual connections is that they're obviously very popular. They obviously work very well, but there's only one sort of like stream of information at any point in time, right? So if you get like your 1,000-word sequence of tokens, those all get compressed into one little stream that goes through the model. In these lock examples, going back to that, it's like you have your like 10 different locks, and between each lock, you only have one little stream that connects them all, right? That works pretty well, but wouldn't it be nice if you could have maybe like 5 little streams or 10 little streams running in parallel so that each of them can sort of convey a different bit of information? That would be much more efficient, right? And so then the idea that came out of ByteDance actually a year ago was, well, rather than just having one residual connection, let's have like 10 or 20 in parallel. And now, rather than just having one connection, we have 10 different connections between all of the different module blocks. That conveys much more information, right?
And is the goal with that, Rich, to increase the gradient ability to update to make the resulting model of this trading process more accurate, or to increase the actual throughput, like decreasing the latency that we have on a chip because we're adding these additional mathematical operands that can be happening in parallel instead of having to like block one after the other?
I think it's more towards the latter part of what you said. And the idea here is that the residual connections contain all information that there is about the original input. But your input can contain many different types of information. Like at some level, what you say, there's the
like syntax.
There's the syntax, there's the semantics. And so it would be much more efficient if you could kind of like split that up into different streams of input so that each stream can operate at just one sort of like sub-layer of the input, right? So that one stream is sort of containing all there is to be known about the syntax of the input. The other contains semantics. The other contains maybe, contextual or like knowledge information about the input, right?
So you're basically trying to look at the input with different lenses.
With different
almost,
lenses. That's a better way of saying it. Exactly.
And then like once you've split these lenses out, like if you're trying to actually use a prism that takes this input and then converts it to these different things, you can manipulate those streams independently before maybe consolidating them back in a white light at the end.
That's exactly the idea. Yeah, that's exactly the idea. So it's just much more efficient. And so if you can do this, the idea is that, yes, it's more maybe like sound from a design perspective to do this, but also you can keep the original dimensionality of the original residual stream. But now that you've chopped it up into smaller streams, your computer can process those in parallel and do faster computation, right? So that there's also the computational advantage to this. And so the hyperconnections paper that came out of ByteDance was in some sense a response to some of the GPU restrictions that were placed on China and them trying to come up with new efficient architectures. And we're going to talk about this in a little bit. That made a pretty big splash last year when it came out. It was pretty popular, but the issue fundamentally was that we hadn't really figured out how to train models efficiently with these multiple residual streams with these hyperconnections until the MHC paper came out of DeepSeek. Because the issue with these hyperconnections is that they make the gradient flow a little bit more complicated now, right? So just like we were talking with the metaphor about the game of telephone, imagine that you were, rather than just passing one message to the next guy, you're passing like 10 different messages down the line, right? It becomes much more complicated to do that effectively.
Totally.
So what DeepSeek did here is they basically came out with a way of making it so that, sure, you can now pass 10 messages down, but there is a certain constraint that you put on the structure of these messages.
And basically, just to like take that metaphor to the extreme of what we're saying, we're basically saying that in telephone, we're passing 10 different words, but related words down the stream. And sometimes those words can conflict in vibes with one another almost.
Yeah, I guess that's a way of putting it.
Or if, everything is positive in this lump, and by the time you get to the very end, you're like, okay, well, what is the sentiment? You'd be able to say, oh, well, obviously it's positive, therefore I should move in this direction. But if 5 are kind of positive and 5 are kind of negative by the time you get to the end, i.e. the gradients conflicting, that's what becomes so hard about trying to consolidate the different things, right?
That's right. What ended up happening in practice when DeepSeek tried to do the normal hyperconnections approach is that it would sort of get really good at doing one game of telephone, but stop doing the others, right? And so how do you basically tell your model, hey, we have these 10 games going on at the same time, focus on all of them simultaneously and try to make sure that the gradient is flowing through all of these like 10 connections is a little tricky. And it's really hard to do that effectively.
You see the same thing in mixture of expert collapse.
Yeah,
right?
Exactly.
Where you often have to actually set in the load balancing strategy that you're doing across these different expert heads. But I'm wondering if that's almost a similar intuition here, right? Which is sometimes things can become greedy and saturate at the expense of other things just because it's kind of all else the same to the model. Like you're penalizing it or rewarding it the same to just really focus on one versus focusing on all of them. So it's going to do that because it might be easier.
I think that the issue here is fundamentally the same, which is how do you create these conditional streams of computation in your model? And how do you have all of the streams used by your model effectively? So just like in these hyperconnections, the idea of mixture of expert models is that you can have one model, but basically at a certain layer, the model can decide of its available compute, what subset of the input does it want to send to each of these sort of like expert heads, right? And so the idea is very analogous. And one of the issues with training mixture of expert models is that sometimes the model will just say, hey, I'm never going to use this one head, right? So here it's the same thing fundamentally. The mixture of expert models is a little different from these hyperconnections because the hyperconnections sort of like permeate the entire model. So what DeepSeek did in this paper is they figured out a way to basically create a constraint so that when the model's training, it has to basically put the same amount of attention or the same amount of focus on each of these different residual streams so that no single one can dominate, right? And creating these constraints, like how do we constrain the model to learn in a certain way, that is honestly like the holy grail of training models effectively. Because models fundamentally are black boxes. Like we can't tell them how to train. They're just going to learn the way that they want to learn, right? And the issue with training models is like sometimes we do want to basically tell a model, I want you to learn in this way. But because they're black boxes, you can't really just write an if statement into the code, right? They're just going to learn whatever they want to learn. So DeepSeek was able to pull up this like paper from the 1960s and find this algorithm that forces these different residual connections to, by this algorithm, basically take the same amount of learning signal effectively and pass it through these different connections in a way that doesn't allow a single one to dominate. And it's a pretty clever algorithm because there are no if statements. It just operates at the level of linear algebra. And they were able to figure out that if you multiply these different residual streams in just the right way, you can enforce there to be this constraint on the model so that these different streams, so there's not like a single one that dominates fundamentally. That was the big like enlightenment here from this paper. I'm curious whether it's going to make it over into American models because it doesn't seem like Anthropic or OpenAI or any of the folks working at Gemini have really said, hey, this is a big breakthrough. We want to incorporate this into our models, or at least no one has like outwardly expressed much interest here in the US in these sorts of architectures, which I find interesting.
Mm-hmm.
To what extent do you think that this advantage that China has built for itself in like developing these new architectures, to what extent do you think that might also be an advantage for American labs? Or do you think that this is just like something that's going to stay in China because we don't really need it because we have like sufficient compute here in the US?
I think if I had to put money on it, I'd say it's probably not going to hop over the pond, at least not quite yet, because the models that are being deployed right now have such different constraints when they're in the US versus in China. I think one thing actually about DeepSeek is they're really going for this end mile consumer application of people that are booting this on consumer hardware, or maybe like very low grade gaming GPUs, fine tuning some things or just using them right out of the box. It's not really made for this super centralized data center use case as much as some of the other models are. And I think in the US, we're really investing in two things. Like one is scaling up the architectures themselves, like much bigger models. And I think the other thing is hardware itself that is really optimized for these transformer architectures. That's what Etch does. That's what Cerebras does. That's what Grok did before it got bought by NVIDIA. I think there's kind of this sense that having generic processing units in GPUs is maybe not the right way to go at inference time. And it's actually going to be way better to have customized things. And I think once you reach a certain speed of inference, you're not really blocked by the model's throughput as much as you are by other things. Like once you get token times down to 1,000, 10,000 tokens a second, you're really running into like API latency at that point to do anything that's interesting, or like how long does your compiler take to run? It's not really on the language model itself at that point. So if this is shown to increase the accuracy of the model, then I think that's a big reason to do it. I think if this lets them train for more steps, that would also be a reason to do it, which kind of ties to the accuracy point. If this is purely a measure of inference efficiency, and I think actually I'll say something stronger, which is often these sparse approaches to building models actually ends up hurting performance because you're taking something away.
Right.
It's like instead of doing n squared computations, you're kind of chunking them into smaller n, and then the n squared of that becomes a lot less. So I think there's such a fight in the US right now for we're trying to build the biggest, most accurate models possible, deploy these for like enterprise level use cases, because the way that you actually get attention is by competing against others on these leaderboards for accuracy. Then there's not really any incentive to invest in approaches that might hurt your ability to do that, which is why I think we're still mostly using dense models.
Yeah.
I think sparse models will have their day.
I mean, there are a ton of linear models that have come out recently, but I think you're right that like Mamba, right? These state-space models, I think they kind of tend to just be like an academic exercise. I haven't seen any big labs actually adopting them.
It's like Cartesia.
Cartesia,
is the obvious
I guess.
ones because it was their model.
Right.
But
still, like as far as I'm aware, no one is really using state-space models at the level of, these big foundation models. Like they tend to just use deep transformer blocks.
Totally.
Yeah.
Because I think they're proven. You know what I mean? It's like until the scaling hypothesis really starts to slow down or break, which I think it will at a certain point, quite honestly, or the compute is going to just be so dramatic required to get to the next level of the scaling hypothesis that I think we're now starting to switch back into this mode of considering other approaches like learning regimens or sparsity or something that allows us to like train better models. And maybe with increasing interest in private solutions and on-device learning, sparse models just for the inference side of things are going to be that much more important. It's clear to me that that's what DeepSeek is really trying to get a niche into, because all their research has been about efficiency. It's not really about the other questions of like model accuracy. They're like, let's be competitive. Let's be in top percent or 2%, but let's really go down this like efficiency.
Down this efficiency route.
Yeah.
I think another thing that has to be said is like, do you remember the lottery ticket hypothesis paper? The idea here of this paper was to basically show that if you have a model that's been trained for a while, there's actually a subset of the connections of the model that at each time are only responsible for creating that output. So it's almost like if you have 1 million weights and you pass in some input, it actually turns out that you could only use 1,000 of those weights or 10,000 of those weights and get the equivalent output, right? So it's like a lot of the weights are actually redundant in a network. But the issue is like, how do you find those sets of weights that give you that output? It's unclear, right? But what that paper showed is that in theory, you could get the same performance with a much, much smaller model. And so having that information, having that insight that actually a lot of these weights are redundant has sort of been this like driving hypothesis for a lot of labs to try to experiment with models that are much smaller and that could in theory get the same performance as a bigger model. The issue is like, in some sense, you need a big model to be able to have a submodel that almost like lives in that big model that gets that performance. It's this chicken or egg thing where it's like, in order to develop a small model that performs as well as a big model, you have to develop a big model to then uncover what the small model was. But that defeats the purpose because then you train the big model. You know what I mean? But
then it would be good for inference.
Then it would be
like
good for inference. Yeah, exactly.
It doesn't help you training.
But like the fact that that information exists, that knowledge exists, that like you don't really need a big model in the first place, acts as this like motivating holy grail for a lot of companies to say, well, if we can be the ones that figure out how to just train a much smaller model, then we can save on compute time. We can save on the money it takes to train these models. So I can see this also being almost like this motivation that in some sense drives these companies to spend all this money to train more efficient models, but that maybe it's like this false hope almost. Yeah.
It's almost ever elusive, right? It's
exactly.
The fact that we actually do have this somewhere within the weights if we maybe just look or can
It's like Atlantis, you know, it's like where people,
that's right.
But unlike Atlantis, we know that it is true that you could find a much smaller model that performs the same as a big model. But it's like, how do you get to this like promised land, this promised small model? That journey is still very elusive, and we haven't quite figured out how to do that.
Yeah.
And I think China is saying, well, let's take a stab at that. Maybe we have that little advantage. If our advantage isn't in access to GPUs, maybe our advantage can be in like finding a way to get to this like promised land where we can train small models very cheaply, very efficiently.
Totally.
And if we can safeguard that IP, then we can have an advantage over American labs.
Well, and that's clearly the niche that they are carving out for themselves, right? And which I feel like also is incorporating the strategic priorities that both the CCP are pushing, but also private industry, where I think it's roughly that NVIDIA is 2 years ahead of China is kind of the general thinking of actually building the chips that are more efficient. So NVIDIA's chips from 2 years ago are more or less the chips that they are building domestically right now. And like conceivably, if progress keeps up, that'll remain true. But there's this big push to actually get domestic silicon. Much like, honestly, the US is trying to onshore a lot of our own silicon manufacturing. That also is the case right now in China too. I think that puts pressure on saying, if we want to be able to serve models that are like comparable quality with domestic compute, we're going to have to get more efficient models. Like that's the only way. I think honestly that's kind of interesting because like train time regimes, they're clearly still using NVIDIA GPUs. I feel like that's kind of the wink, wink, nudge, nudge with all of this is they're either using the ones that are branded, these like H80s in NVIDIA, or they're actually smuggling in like H200s. But regardless, I think like train time, they're still using these NVIDIA chips. The big scale out you're seeing stateside right now is in making those for inference clusters. It makes sense that China would be thinking the same thing. It's like, maybe actually it doesn't matter. Once we find this lottery ticket during training, that's on a relatively beefy compute cluster, but we're like really strapped on this inference side of things. So we're trying to solve that problem. Why the US isn't picking up on a lot of these like sparsity advancements, I don't know, other than like the accuracy argument that I was making before. But I do think it's just kind of an interesting footnote that the things that we do immediately pick up from China, like from DeepSeek, GRPO, right, are on the train time and accuracy side of the equation versus things like this. I wonder if that holds for more examples than I'm thinking of right now, but it definitely seems like if you have something that's going to be competitive for the train, like actually for the parameters of the model that you're going to ship, like we'll suction that up immediately. But things that are a little bit more like, there's some trade-offs associated with this approach. Like linear attention is the same thing. It's often good, but not quite at the same bar as quadratic. That's a little bit too much of a compromise. I think things that are like flash attention, that are a little bit more like apples to apples, this is like numerically the same, it's just a lot more efficient, are things that American AI labs say, well, let's obviously adopt that. That's Pareto optimal. It's like obviously better. This trade-off question, I think very few labs right now are willing to make the trade-off.
Yeah, Americans don't want to have to make any constraints. Yeah, you just want everything. Yeah, we just want to have our cake and eat it too. I think that's interesting. The one thing that I think we haven't seen at all is us adopting a Chinese evaluation benchmark and tested that out in the US. You know what I mean? Like, it's interesting that I feel like the US still very much leads the race when it comes to developing new benchmarks and new challenging benchmarks. I haven't seen any other country come up with a very compelling universal benchmark in a way that's comparable with the US at all, right? Like we have coding benchmarks, like math benchmarks, like general reasoning benchmarks. All these things have largely been innovated in American academic labs and industry labs here in the US. And I just find that that's kind of interesting. You know what I mean? That like we have created these two different streams of independent research that different countries are starting to specialize in. I wonder if that's also going to be the case for once European labs become a little bit more mature, like if European labs are going to focus on a different type of like research stream more than American or Chinese labs. Like it's still a little unclear.
What do you think their niche would be? What niche should they be?
You would have thought that, I would have thought it would be like privacy preserving or like data style things, you know what I mean? Maybe like testing for like bias in models or like these types of benchmarks. But even those I'm seeing mostly come out of American labs, which I think is interesting. So I'm not entirely sure, but I think it is really cool to see, Chinese labs really like take the vanguard when it comes to efficient LLMs. Like that is a little unexpected, I think, because I would have expected Chinese labs to be the ones like really scaling out things and almost American labs being the ones that are looking more at efficiency. It really seems like the script is kind of flipped. The other thing I want to talk to you about is the second paper that came out of DeepSeek, which is the Engram paper. Did this like pop out on your radar over like winter break or these last couple of weeks?
I think it was actually front page Hacker News when it first came out.
Oh, was it? Okay.
Yeah. A lot of people were talking about this. This is kind of the idea that like instead of one representation of an input token space, you can potentially have multiple ones. Also, it's spelled Engram, which I find kind of annoying because there's also the N-gram, like the letter Engram.
Yeah.
Which is multiple words in a sequence. This is not really saying that. This is more just like they're different representations of one token.
If I'm not mistaken, the way that it's spelled, like Engram, is a concept from psychology, I want to say, or like a neuroscience kind of based thing.
Yeah, it's a hypothetical permanent change in the brain accounting for the existence of memory.
Right, exactly. Yeah. But you're right. I think Engram and Engram are definitely like some like play on each other.
Totally.
But it can be a little confusing. Yeah. So basically, the big insight is that if you have a language model seems to have some sort of notion of knowledge, right? Obviously, because like you pass in some input, you ask it a question like, what's the capital of France? And it outputs Paris, right? So it feels like, okay, well, this model has some sort of knowledge. But the thing about language models is that they're able to access this knowledge via computation. It's not like the knowledge is stored somewhere in the model. The model has to take the input, run it through multiple transformer blocks, run it through this residual stream that we were just talking about. And as a result, as you process the input through several transformer blocks, at some point, maybe at layer 7, layer 8, it'll have in the residual stream, what'll bubble up is that the answer to your question is, in the case of the question I asked, what's the capital of France? Paris will somehow appear in the residual stream, right? Like
it's truly so inefficient if you really think about it.
Yeah.
It's kind of like going to chat instead of Google searching something that already exists online. It's
exactly.
Like there is just a static, doc, a .txt that's hosted on some server somewhere. Why are you having ChatGPT generate you a new one? It's kind of the equivalent, right? It's like this knowledge actually is out there and cached. And if we just had some like querying syntax of being able to do this at a SQL layer,
exactly,
for instance, it would be so much more efficient to do that.
Exactly. You're like reinventing the wheel each time is the thing. You know what I mean?
And for each token.
Yeah. So it's ridiculous. So like when you ask a model like, hey, what's the capital of France? Maybe we don't know this, but maybe what's happening is that the model is first going, okay, well, let me first understand what is the syntax of the sentence. What is the capital? Okay, so I can see that this is in English. Okay, I can see that there's a verb. There is a entity called France. What is France? Well, in my training data, I know that France is maybe a country. Okay, well, what's the relation between country and capital? Oh, capital is a city. Okay, so city, country, France. France, what is a city in France? Marseille. Is Marseille capital? No, Marseille. All of that is happening thousands of times in the model. And then finally in layer 8, layer 9, layer 10, it'll start seeing the word, hey, Paris. Paris could be a good fit. Could Paris be a good fit, right? So the model's doing like all of this like introspection and thinking, but it doesn't have to do this, right? Like we have the answer. Like somewhere out there is the answer that Paris is the capital of France. It's like a yes or no, a binary thing that you can look up, right? So the insight that DeepSeek here had was that, hey guys, well, rather than having models go through this painstaking process of accessing memory via many, many steps of computation, let's just have there be some kind of a knowledge base out there so that rather than having to like do this hard work every single time, if you have a question like, what is the capital of France? What if we just stored an embedding relating France and Paris? And at the very first layer already, the model can say, well, let me look up in my knowledge base. Is there anywhere in my knowledge base where I'm relating France with its capital? And very likely it'll immediately hit a cache hit, right? That gives it back the embedding from Paris. And so this isn't like the model gets the answer directly from its knowledge base, but rather at the very first layer, it can access a embedding that represents the answer and put that into its residual stream, the same residual stream we were talking about just earlier, and have that be in the residual stream from the get-go so that going forward, it doesn't actually have to do much more work. It doesn't have to do any more computation. It can just kind of feed the input directly to the output layer and just output the answer, right? What you're storing in this knowledge base isn't just the actual answer. You're storing basically a representation that you can directly pass to an output layer that will output the word Paris in this case.
I almost think of it as kind of like a helpful hint. You know what I mean? Because in theory, right, you actually do still have to go through, and this is very like pedantic, contrived example of saying the capital of France is Paris. If we have already encoded that whole sentence already, and we're trying to predict Paris, if we give the model that context, it still actually does have to calculate all of these interim transformer blocks by doing that math, right? Just because like it's not sure if that hint is necessarily going to be the answer. We can't fully cache it or have a no-op. But in cases where, you know, there's some much longer source of hint, like maybe in a programming language, there's some documentation for what this function does, right? If we can derive that this function is relevant and maybe even have some captured dense state of what this function does and feed that in as a hint, we can avoid the model having to itself churn for like 50 tokens or like 100 tokens in order to come up with that context to like refamiliarize itself from scratch. It instead just has that and then can actually get to making the hard work, which is coming up with some novel thing that's based on that function.
I have a good metaphor for you.
Please.
Okay. So it's like, you know, in a restaurant.
Does it involve locks?
No. This is a food metaphor because I'm
because I'm hungry.
Because I'm hungry. Yeah. Okay. So you know, in a restaurant, right? Restaurants are obviously cooking a ton of different dishes every night to serve their patrons. The only way that restaurants work is by having basically chefs come in early in the morning and do a bunch of food prep, right? So chefs will like cut up all the onions already.
This is a great metaphor.
Cut up all the garlic already, right? Make the marinara sauce. Let's say we're at an Italian restaurant, okay? Make the marinara sauce, right? Roll out a bunch of dough. So when an order comes in, rather than having to like cut a new onion, cut some garlic, put some tomatoes to make a sauce, you can just take a pan, add in some olive oil, like your pre-chopped garlic, your pre-chopped onions, cook it for like 2 minutes, add the sauce, and then you're done, right? Easy peasy. This is basically doing that. This is basically saying, hey, we're not going to store the entire dish, right? In the knowledge base, but what we're going to store is like these individual like pre-packaged ingredients already so that the language model can just take these things from the metaphorical fridge and just very simply combine them together and not have to do any of the work of cutting these ingredients up and pre-processing them. And I think that this is actually really interesting because, yes, you're right that currently this is a way of basically like pre-processing this information and speeding it up, but the model still has to go through the different blocks. But in the future, you could imagine that, this could be combined with another method where the model can decide to not go through subsequent blocks and just stop computation early and then pass it out to the output layer. This conditional deciding when to stop processing an input into the model, this is a known thing that folks have done. It just hasn't worked very well in practice yet. But if you could combine this idea of pre-processing these embeddings in a knowledge base, you could imagine like a whole new world of different architectures where models actually don't just have a fixed number of transformer blocks, but can dynamically decide when they need to keep producing more computational steps and when they're done, right?
That would be kind of cool, right? It's like you literally set some like lambda weight to this residual stream and have that dynamically adjusting 0 to 1. Do we actually count this? Do we not? That could be at train time to make it efficient, trainable, and back probable. But at inference time, if a model is coming back and self-describing its own lambda as saying, this is 0.002, then just don't run it. Like actually make that kind of a deterministic fork
Exactly.
at inference time that changes the model, quote unquote, but it's informed by that learned hyperparameter at train time. That's conditional.
And this is a different type of conditional computation. In language modeling, we've thought about conditional compute for a while. So chain of thought reasoning is typically
Very
how we think of conditional
totally.
compute. Yeah. So the idea of chain of thought reasoning is like the model can decide when it's done producing an output by basically like self-reflecting whether or not it's like actually answered your question, right? But this is at the level of like each individual token can decide if it's done producing output. What this conditional compute here is actually different. It's at the level of like how deep or how complex the model is. And these two things are almost like orthogonal, like they can both happen simultaneously, right? You could have a model that at the level of the complexity of the model is conditional, that can decide when it wants to add transformer blocks and when it's done. And also at the level of like in the output sequence, when it's done outputting something. And in some sense, this is totally in line with the previous paper. DeepSeek is here trying to come up with new ways of doing conditional computation that saves on compute time and inference time costs. And again, I think it's induced by the fact that Chinese labs don't have as much compute as American labs.
And can you say more, Richard, about like how these embeddings are actually created in the first place? Do I just give the model some in-memory budget to say, you have X slots of cache space available, and during train time, you can choose to write or read from those caches at will? Like, how are they actually instituting this cache that they can then draw from in order to do these residuals?
Yeah, so at train time, what basically happens is that the model looks at 2 or 3 sequences of words at a time, processes those, and basically gets to decide how much it wants to write into the cache, right? So it pre-computes those. It takes like the final output of the model for those 3 words, hashes those, and writes those into a cache. And it does that basically for sequences of like 2 to 3 words at a time in the training data. And over time, as it does this more and more and more, it basically builds up a mapping, like a dictionary of sequences of 2 to 3 words to their embedding at the final layer of the model. Does that make sense? So that then basically at inference time, if it's trained for long enough, it will have seen a lot of different combinations of words. And at inference time, there's a good chance that the subsequent 2 or 3 words have already been seen during training, and it can just take the embedding for those 2 or 3 words and use that embedding
as its helpful context.
As its helpful context.
Basically.
Yeah, exactly.
I honestly kind of wonder if you could have a permutation of this architecture that's a little bit more like a conventional programmatic I/O interface. Like, it's probably not back probable in a way that makes it easy to do. Maybe even wouldn't be plausible to institute in practice, but like there definitely seems like something here about the RL environment of it all. If there's some sandbox you have access to during train time, and we actually want to allow the model to be able to like write and read something from a deterministic data structure. It feels like we're kind of still operating this like continuous, smooth landscape for training, just because that's actually what is back probable. You can like get the gradient of that and derive it. In concept, you almost think of like this memory store as wouldn't it be so useful if, much like you can write to a document and know that that's never going to be permuted, the model could just put things into it at certain intervals of time and then know, okay, this is like my hash index that I get back from this file. And if I ever need to reference that, it's just an easy O of 1 lookup call. I wonder if they could do something like that.
Yeah, do you remember there was a paper in 2016 called like the Neural Turing Machine paper? It was trying to reproduce a Turing machine, which is like this hypothetical machine that like Alan Turing came up with in the 40s, a universal computational machine. And the idea is like at every output of the model, at every time step, the model can decide whether it wants to read into cache, delete from cache, or write to cache.
Mm-hmm.
And that's basically it. And you do this via different like gating mechanisms that you can learn. So this idea has been around for a long, long time.
It's just really hard to pull off.
It's just really hard to pull off. And you kind of run out of space if you do it naively, right? You only have so much space and these embeddings are so big that your cache is fairly small. And so what we do in practice now, I mean, there's many different types of ideas that we've developed for how do you like encode knowledge or like a storage system in your model. In the US, what we've mostly focused on is this idea of like a KV cache for inference. The idea that you can like cache the previous history so you don't have to recompute it each time. You can just like access it directly. But the issue with that is as you add more and more context, eventually that KV cache just keeps growing and growing and growing. And so that's not really scalable either. So the idea that you could have some sort of like an actual database or knowledge graph is actually very compelling, I think, here too in the United States. And unlike the MHC paper that we were just talking about, I could actually see American labs like copying this a lot more because this isn't just a compute time consideration. Like this is also a way of encoding data in a more like a more structured way than we currently do. And I could see there being a compelling use case for a lot of companies here in the US that are doing RAG-based sort of like knowledge retrieval stuff, incorporating this. And I could see this like actually helping at those helped well, you know?
Yeah, so could I.
So I don't know, man. I think China's doing some really interesting stuff, man. I wonder to what extent this one is actually going to make it into the US. Do you buy this idea of like conditional memory as like a new primitive that exists in the world now? We've had like the idea that like attention is like a primitive in transformers and that mixture of expert models or like these mixture of expert heads are a new primitive. Do you think that like conditional memory like this could be a new like primitive that is part of every transformer block going forward?
Yeah, I mean, maybe, right? I think it kind of comes down to the Americans as to will this actually increase the accuracy on some task versus just spending more on compute to have things run longer or waiting a little bit longer. And I think as you see with people choosing to use Opus over Sonnet or 5.2 codecs over 5.2 regular, people seem to be willing, especially in asynchronous loops, to just wait longer for the output if it's going to have higher accuracy because it kind of just like compounds and builds off of each other the more steps that you have. So I think the strongest pitch that I have for memory is probably in corporate situations where there are things that would be inefficient to actually store within the memory. If you're trying to encode these into your context window, it's going to be even longer than Anthropic's constitutional AI report. You know, it's going to be like 100,000 tokens or like 1 million tokens or something. It's just not really efficient to actually put that on the attention window. There's some built-in trade-off that seems intrinsic to all of these models, which is that the second that you're talking about memory in some construct that then you use and do something with, you're necessarily talking about a loss of fidelity over the actual representation of that memory. And that's obviously what humans do, right? It's like we kind of have some sense of how my code base works. I couldn't tell you every single line of my code base from memory. That would make no sense. Yeah. I instead would familiarize myself with a context once I have the memory. I'm like, this is the file that I think is going to be relevant based upon the mental model that I've built up. And then you refamiliarize yourself with the code. In that way, transformer architectures and all LLMs are like kind of unhuman because they rely on the attention window having this full fidelity representation of exactly what is there that we can then do operations on. And, you know, Anthropic did some work on trying to look at the transformer circuits, is what they called them, of these like original primitives that are learned by the models first before other things. And they found that this copy primitive ended up being one of the most fundamental things. You know, it's like the first thing that these models learn is grabbing something from the attention window. Exactly.
Yeah.
Like
and then like copying that into the output.
Totally. Yeah. Which seems obvious because we've seen it done so many times with like full reconstruction accuracy. But in some ways, it's actually like not trivial because we're feeding in the model's embeddings and having it output logits, which are just like one-off mappings. It's not really apples to apples. You can't just like do a pass-through identity function and get that same output. So we found that it's very useful. It's very easy to train these things in practice to be able to regurgitate exactly what is like in the attention window. I think with all of the memory thing, we're basically saying like, is a fuzzier notion of memory useful in these situations if we're trying to like update the vibes of a model or adding things that are not otherwise able to be encoded within the limitations of the KV cache? I kind of think that that fundamentally is like the niche that they occupy. Exactly how that tracks to industry, I think, is like a pretty interesting question, because there don't tend to be a lot of problems in industry that you can't distill down to one model that has some prompt.
Yeah, it's true.
Right?
It's true. Like LLM as a judge right now is so popular. Like the idea of like using an LLM, prompting it for whatever you want, and using that to like train your own bespoke model or like fine tuning it in some little ways. That is kind of like what the current state of the art is, right? No one is really training a model from scratch anymore. Everything is just either using a big model and leverage that to train a smaller bespoke thing, or just using the big model if you have the money for your given task, just prompt it in some clever way.
Mm-hmm.
But I do think that fundamentally there are going to be interesting plays in the future, like we were talking about Apple on the last pod. I think there's some play here for models that still live on device or like personalized to a given user in some ways, and for companies to try to like innovate at that level in some clever way, right? So that there's like maybe a core model, and then there's like a conditional model for a given user, like that model that has like conditional access to some sort of memory or something like this.
I think one other thing, honestly, might just be the auditability of these pipelines. Like I'm thinking McKinsey, right? Big consultant, like the Big Five company. They have a case study history book of all of the cases that McKinsey has worked on historically.
Oh, like their McKinsey method?
Yeah, exactly.
Is that the method?
That literally is kind of the method. It's
Yeah.
like they've been around for so long and have been utilized by so many firms that like fundamentally business has not changed that much. It's kind of the intuition, you know? So it's like if something worked 30 years ago, it's probably still going to work. If it worked like 2 years ago, it's almost certainly like still going to work. So they basically have this like database of all of their past cases written up with a ton of fidelity, ton of diagrams, outcomes, learnings. They follow up. They try to get very like data driven about these things. And as an analyst or a partner, you can query this database when you have some new consulting projects. So you're like, you know, we're consulting with some telco.
Right.
We've consulted with this other telco. What did we do with them? And like, will it work in this given situation? You're kind of like trying to apply the past to be prologue for the new thing. I honestly think that that's maybe one situation in which these memory-based approaches could actually be a value add over existing architectures themselves. Because one, there's so much in that database. You can't just encode that all into the attention window. And maybe you want to like learn more like latent subtle themes than just like the text alone would lead you to believe. You kind of want to get to some higher order notion of themes. But you don't really want to train your own model to learn those things, because even if you have the talent to do that, if your model gives you some answer, like they're clearly known to just hallucinate origin. Like it's very hard to be able to say, I'm going to give something at train time and then have the model tell me where it got that at train time. Once it's in the weights, it's kind of lost to the sands of time. You know what I mean?
Yeah.
I almost wonder if memory in this way could actually be used as an audible pipeline where you say, I have these like bits of data that I want encoded in my memory.
Oh, interesting.
Where each case is like one unit of memory. And then because it's in this tertiary system, you're actually relying on the model to tell you what memory to index into. And then that would let some deterministic system say, hey, I know that this output leverage these 5 different inputs, because that's
really
actually
cool.
what the model told me to do, you know?
One of the problems when you have like a very big database is like you'll have a multi-tenant system, right? Or like you'll have different folks using your database, but you only want certain folks to have access to certain data. Like you could imagine this is also one of those ways that you could have a model only have access to the data that a certain person should have access to.
Exactly.
Right? Like this sort of thing.
And block that hard.
And have a hard block on that. Yeah, exactly. And this is kind of what RAG has been trying to do a little bit by integrating with row level security based SQL systems like Postgres, for instance, right? So you could have like a system that uses RAG where the vectors that are stored, that the RAG system queries are stored using Postgres.
Yeah, like those are the rows, and you're like querying, filtering.
Yeah, you can kind of like impose
Yeah,
like certain constraints on your database via the built-in Postgres row level security systems.
Yeah, I guess the question is like, is there a niche where RAG doesn't really work for you? You need to like find these deeper relations, but those deeper relations can't actually be in the model weights for whatever reason. Like maybe you would lobotomize the model and would start doing things that you don't intend if you expose it to this data, or like something.
Interesting.
For the model to still cultivate some vibe of this data. That's like the memory, but not actually need the like high fidelity thing in practice before it consults this like tertiary data store. I'll put it this way. I don't think we've found the super app for memory. We like haven't really found the product market fit for memory applications that are outside of these existing RAG document-based retrieval pipelines.
I think that's true. And another thing about RAG is like the original RAG paper was like proposing like this way of training a memory system in conjunction with the model at the same time.
It's true.
But no one does that anymore.
Yeah.
Right? We've all gone like, hey, this is a cool idea, but like the original approach like is too complicated. Let's just like freeze both the model and the knowledge base system as two frozen separate systems and have them interact with each other, but not like in some way that like they're both joint training or learning from each other. So this is basically like more of the former idea that RAG suggested, which is like, could you train your knowledge system at the same time as you're actually training the language model? And I think that's kind of cool. Like we're going back to that original idea, and I could see that actually being successful.
Mm-hmm.
But for whatever reason, like RAG's been like super successful as it's currently done. You know what I mean? As like two frozen systems interacting with each other without actually learning jointly.
100%.
Yeah.
Yeah, I think the main thing this is giving you right now is the efficiency.
Yeah.
You know, being able to do the same level of performance or maybe like slightly worse with way less memory. And, you know, honestly, I think there's a threshold at which even like the frontier labs are probably interested in sacrificing like 0.1% on some benchmark for like way faster inference, way less compute, because that charges them money. And if they can command the same kind of market pricing premium and just drop their cost basis significantly, then like they will do that. I think that will cross the international date line. We'll see if this other stuff does.
We'll see if it does. Do you think you would use it if you were developing a foundation model at this point?
I'm certainly interested in the sparsity stuff more broadly. I mean, I think that there's like totally a niche for that. I think on mobile, like on-prem hosting, there's definitely a niche for that. Some of the memory specific stuff, I think kind of TBD on like where you deploy it, to be totally honest. The jury's still out on that, but a lot of the optimizations that I think they're making more broadly to do the same level of performance with way less compute, I think is super useful. Also useful for like distilled models, like fine-tuned use cases where you actually want to like fully train some parameter set. Way easier to do even like the fine-tuning use case on a smaller model than to use some bigger one. You don't even really need to use LoRa or any of these adapters for efficiency. Yeah. So I think the inference case to me is like super strong. The additional functionality that this like unlocks for your average Joe, I think is still kind of TBD. And we haven't even touched on the fact that memory can actually hurt performance of these models in some way, where if it learns something bad in memory, especially if that's untested with the model providers, that can result in worse performance for you. Whereas if you start from a fully clean slate, that's obviously how the eval benchmarks work in the provider labs. So there's a lot of like organizational complexity once you start introducing these additional factors that are outside of your control.
It is kind of nice though, because like memory also lets you do like patches and version updates. You could imagine like you have the base model and you just update the vectors that are in memory, right? To like improve those a little bit, or you can like have a little bit more of it's kind of like an artisanal touch to the model. You can kind of tune it ever so slightly by tuning the vectors in this database a little bit more. But you're right. I mean, it is another layer of complexity to the existing pipeline already.
Yeah.
So we'll see, man. Well, either way, I'm stoked for DeepSeek V4 whenever it drops. It's probably going to drop around the Chinese Lunar New Year. That's kind of like the...
there you go.
That's the...
Happy Lunar New Year, everybody.
Happy Lunar New Year. I don't know when it is exactly. Do you know when Lunar New Year? I think it's like in like February or something like that, I want to say. Whenever it does come out, we'll definitely make sure to...
February 17th.
February 17th.
Look live, people.
Hell yeah. Maybe we'll have some dumplings on that day.
Yeah, what year is coming up?
I'm going to go rabbit.
Horse.
Oh, I was about to say horse,
sorry, buddy.
Man. I was about to say horse.
Of course you were.
What are we right now? Is this the year of the snake?
This is the year of the snake.
The year of the snake. That's right. Interesting. All right.
We've got dog, chicken, monkey, dragon, snake, ox, rabbit, rat.
What are you? Are you a monkey?
Like when I was born?
Yeah.
I don't know. I'm a little squirmy. I could see him being a monkey.
I could see you being a monkey.
Like a good bonobo.
A good bonobo.
Yeah.
That's right.
Yeah.
That's great. Like a little chimpanzee. I
That's
could see that.
exactly.
I could
Yeah,
see
exactly.
that.
I don't know. 95. Let's see. It's not pulling up.
It's not pulling up.
This is where the LLMs are failing me.
Oh my god.
I thought Google
dude.
would have this on lock. They
Oh
don't.
my god.
Oh god.
That's all right.
Anyway,
we'll figure it out at some point.
Yeah, that's true. Happy almost year of the horse.
It's pig. I just looked it up. Anyway.
It's pig.
Yeah.
Next year?
You're pig.
Oh, I was pig.
Yeah.
Nice.
I'm not calling you a pig.
What,
I'm just like,
what else?
What's up, dude?
All right, this is devolving.
All right, man. Well, I'll talk to you soon.
Sounds good. Till next week.
Till next week, buddy.
Later,
All
Rich.
right. Bye.